start the recording. Okay, so hello everyone. Welcome to the tutorial 2 of Analog Integrated Circuits, and I am Chaitanya Kumar, a PhD scholar from Department of IIT Madras. So in the tutorial 2, there was the common source amplifier that is made through a MOSFET was discussed. First of all, its large signal parameters were discussed. Then we shifted to small signal parameters and decided the gain and the things of the MOSFET. We looked at regions of operation of MOSFET, and then we looked at various biasing techniques of MOSFET. The simple resistive divider bias MOSFET we looked, and after that we looked some robust techniques which can prevent the gain variation across process voltage and temperature. So this was all about second week of analog integrated circuits, analog electronic circuits. I hope every one of you have gone through the course material. Now, is there any doubt or any issue you want to discuss in this tutorial before I begin the problems of this session?
Sir,
Yeah.
sir, while in the assignment, what and all circuit for in the assignment week 2 itself, in week 1, if diodes are corrected parallel, but one is forward bias, one is reverse bias, so mathematically and practically also there is a one application because of the like that, and for every circuit there would be a meaning, no sir, in the assignment they given. Is
Correct.
it possible? Is it possible to explain notes for every for problems?
Okay. Do you want to start with first assignment or the second assignment?
Second assignment, sir. First assignment I am comfortable, sir. In Vishal sir
Second.
also discussed.
Okay. Second assignment. Okay.
Yes.
Can you share which particular question you want to discuss? Wait, let me check. Is the assignment 2 also the same as the previous one? Just a minute. I'll
Okay,
open the
sir.
course.
The screen share is not there, sir. You are not sharing the screen.
Just a minute. Is my screen visible now?
Yes, sir.
Okay. So let me go through this thing. Wait, I'll share the screen of this. So is my laptop screen visible to all of you guys?
Yes, sir.
Analog electronic.
ITM. Sir, you need to type IATM, sir. No, no. So after analog circuits, yeah, yeah.
Okay. Yeah. Yeah, it is. Just a minute. There is so enrollment ends at 5th February. I can't enroll in this now. If possible, Thalpasai, can you share your screen and present the particular assignment? Or wait, the problem is that we are not supposed to show you the solutions of the assignment. However, we can explicitly tell what particular circuits do. So, if possible, can you share your screen and present that assignment so that I can copy from there one by one and then start discussing them?
Sure, sir. Definitely.
Yeah.
Sir, in question 5, in sir, in question 6, here it is biased with voltage source, no sir. From 6
Correct.
to 7, it come to current source.
Okay.
So means what are the advantages from 6 to 7, and in 7 also, in 7 to 8 there is a modification circuit. How it is going to replicate, I would like to know. So here it is diode connected connection is there. One more resistor is added. How it is going to help, like that I would like to know.
Understood. I will discuss from problem number 6 to 7 to 8 what all improvements are there. Let me copy these into my tablet.
Is it okay, sir?
Just a minute. Then problem number 7. Can you zoom into the problem number 7? Yeah, wait a second. Now zoom into the circuit of problem number 8. Okay. Can you take it a little up?
Is it fine?
Okay, fine, fine, fine. That's it. Okay, now I suppose my screen is visible to you, right?
Yes, sir.
Okay. So let's go through them one by one. The first circuit that we have is so
Common source.
all of these are common source circuits. Okay.
Hmm.
This is a common source circuit. How it is a common source circuit? During the actual biasing, there will be there will be like these capacitors will be open circuit during the DC analysis. There will be some current flowing through the transistor due to the biasing arrangement. And apart from that, what when we go to the due to that, there will be some GM of this transistor. And when we actually go to the small signal analysis, then these capacitors will get shorted. And when this bypass capacitor gets shorted, we have a ground over here. And it's since the ground is since the source is grounded, the input is given at the gate and the output is taken at the drain. This circuit behaves as a common source amplifier. Okay. Similarly, the second problem, how does this looks in small signal? It simply looks like 25k resistor and an input source. Then we have two parallel resistors of some 1.65 mega ohms parallel 0.85 mega ohms. Then we have this C3 is grounded, so the source is grounded, and on top of it we have 0.5k. One this and this will come in parallel. You guys can see how
Yes, sir. Okay, here now. Second
the
slide, sir.
C2. Yeah.
Sir, you can, I mean, you can scroll down a little bit. It is not visible clearly. Circuit
Now.
2, sir. Circuit 2.
Currently, we are discussing circuit one. We
Okay,
will
okay.
move on to circuit two later. So I am
0.
showing like in small. So what I'm trying to establish is that in as far as small signal model is concerned, all the three circuits are same. So first of all, I am just plotting it for like the first circuit, that is circuit one. So here you can see this is how the small signal model look. You give input to the gate of the transistor. It goes through a resistor divider. However, this resistor is in order of some hundreds of kilo ohms, and this is just 25 kilo ohms. So most of the voltage comes at the gate, and you take the output at the drain. So this is a common source amplifier as far as small signal model is concerned. The same goes with circuit 2. In circuit 2, what you have is again you have a 25k input resistor. Before that, you give the input. Now, so this how does this particular branch behaves? This is a zero point 0.5 mega ohm of resistance, and in small signal there will be a diode connected resistor, diode connected transistor over here. Now, can you guys tell me how does a diode connected transistor behaves in a small signal equivalent? What is the small signal equivalent of a diode connected transistor?
Sir, 1 by GM approximately.
1 by GM of resistance, correct?
Yes, sir.
Yeah. So this 1 by GM of resistance will come into series of zero point 0.5 mega ohms of resistance, and 1 by GM is a very small number, so it can also be neglected. This current source will become an open circuit, and at the output you will have
Point 0.5 kilo ohm. Yeah.
zero point 0.5 kilo ohms of resistance. So exact same circuit as this one was posing in small signal.
No, no,
The
sir. My question is here in problem one, we bias with the voltage divider bias, no, sir. Instead of that,
correct
in the circuit two, we replace with uh,
current.
R1 with current source. So we will get in small signal analysis, we will get more resistance. Open circuit means we will get more resistance, no, sir. And here he connected diode connected and one more resistor. Means what will be the benefit of doing
No, in
from this
small, that's what I am trying to tell. In small signal analysis, the both of the circuits are exactly the same. Okay.
hmm,
Even like in small signal analysis also, there is some resistance of like zero point 0.5 mega ohms plus some 1 by gm, which is 1 by gm is almost zero, and then there is a 25 kilo ohm resistance. In this also, this is what is this going to be? 0.85 mega ohms plus in parallel to 1.65 mega ohms, somewhere in hundreds of kilo ohms, exactly same as what we have over here. In small signal, all these circuits behave the same. It's just that in large signal model, that is when the biasing of the model is considered, the second circuit turns out to be more immune to variations in voltages and process as uh, more than what first circuit is immune. Okay, that I can show you how.
Oh, yes,
So
sir. That one. Yeah, my question is
yeah,
that one. Yeah.
correct. We will put these two circuits side by side. So yeah, these two circuits are visible, I hope.
Yes, sir.
So let's forget about all the small signal things that are attached to the circuit. This is an open circuit. This is an open circuit. This is an open circuit. In this and this are open circuit. Let's draw only the biasing, how these circuits look in DC. Okay. If we do that, what we find here is 1.65 mega ohms, 0.85 mega ohms, Then we have a 0.35 mega ohms over here. This is how this circuit looks, correct? And we have 5 volts over here. Okay. Now, how does this particular circuit looks?
A current source and M1 diode connector configuration, and 0.5 mega ohms is connected to the M2 gate terminal.
In DC, does this 0.5 mega ohm resistance matters at all?
No, because of high resistance, but we need to consider, no sir, initial. Okay.
No, I mean, yeah. See, this is an open circuit that it is going to, right?
Yes.
So it does not matter. So you can just remove it. Still, you will have the same result. So this is how these two circuits look. Okay. Now, let's say there is some change in the voltage of this circuit. Okay. The supply voltage that you are giving to these two circuits, let's say there is some change in that. What will happen in the first case? Let's say from 5 volts it drops down to let's calculate the current in current when let's calculate the current in this MOSFET when the supply is 5 volts. Can you do that?
Yes, sir.
So let's try to calculate it parallelly. So what will be the voltage at the gate of the transistor?
Sir, 0.85 mega ohms by 0.85 mega ohms plus 1.5 mega ohms into 5 volts.
So how much this comes out to be?
0.85. Sir, 1.3.
1.3 volts, correct?
Hmm.
Or wait, let's forget about these numbers for now. Okay, let's call this R1, R2, RS, and this is RL. This is also RL. Okay, so and let's call this VDD. Let's not talk in terms of absolute value. Let's talk in terms of like actual voltages. So this voltage is R2 divided by R1 plus R2 into VDD, correct? Let's call this VG. Okay.
Yes, sir.
Now, what happens if this voltage is VG? Can you calculate the current through this transistor? And there is one more condition that VDD is large enough so that this transistor remains in saturation. Okay. We will assume that this transistor is in saturation itself. Now, what happens is, how do you calculate? Let's assume this voltage is Vs, okay, and the current through this transistor is ID. Then what is Vs equal to?
So ID into RS, right?
ID into Rs. Okay. So, and now if the current is in saturation, what is ID equal to?
1 by 2 mu n C works W by L
C of,
VT. Yeah.
just a minute, 1 second. So half mu n cox w by l into vg minus idrs whole squared, correct?
Yes, sir.
And let's call this as k, okay, for now, to simplify the algebra. So it becomes id is equal to k into vg minus vg square plus id square rs squared minus 2 vg id rs. Do you follow this?
Yes, sir.
Okay. So id by k is equal to, so if we talk in terms of id square, we have id square rs squared plus id by k plus vg square minus 2 vg id rs. Okay, that means id square rs squared plus id times 1 by k minus 2 vg rs plus vg square, this equal to 0. So now, like without actually going into solving this and all, you know that this is a quadratic equation, right?
Yes, sir. We'll get two values based on the saturation condition. We need to choose the value, right?
Correct. So you will do all that. So, but can you see that the value of ID will be a function of VG?
Yeah, it depends on VG only, sir.
Okay. Now, what is VG?
It is VDD by R2 by R2 by R1 plus R2.
So, what happens if VDD changes? If there is a variation in VDD, what happens to ID?
Sir, if VDD increases, ID will also increase, drain current.
Correct. If VDD increases, if
Drain.
VDD increases, ID also increases. VDD reduces, ID also reduces. So, and what is GM in terms of ID?
Okay. Differentiation of, okay, yeah.
Root 2 ID mu n cox w by l. Correct?
Yes, sir.
Okay. So, ultimately, what I am saying is that the GM, if is a function of ID, and since id is a function of vdd, so ultimately gm is a function of vdd, the supply voltage. You understand this?
Yes, sir.
So if gm is the function of supply voltage, now if there is voltage variation, suppose let's say you chose the value of rl and gm such that you want what will be the gain in this? Minus gmrl, correct?
Yes, we need more GM. Based on that, we can increase the gain.
Yeah, that is fine. So let's say
Mm.
you designed your circuit with a 5 volt voltage source, and you have chosen some value of RL and some value of GM, so that you can get, let's say, a gain of 5, okay, from this circuit. Now let's say due to some weather condition, some like external condition, your VDD increase from 5 to 5.5. What will happen? Your
Yeah, gain
GM will
will, yeah.
Your GM will change, RL is fixed with a voltage variation, and your gain will change. Correct.
Yes, sir.
So here what is happening is your the circuit, the biasing circuit is sensitive to supply variations.
Exactly.
Understood? Now,
Yes.
let's say what happens in here. What is ID? If this is 200 microampere,
Yes, same thing will reflect out there. Yeah.
same
Current
thing will
value.
be over here. Now, this current source is basically whatever voltage you apply across this current source. If this current source is ideal, we make this current source in practice and we make sure that it behaves close to ideal. Now, even if this 5 volt changes from 5 volt to 5.5, the current, if you are somehow able to maintain this current to be equal to 200 microampere, your current in the main transistor, the common, so the input transistor doesn't changes at all, correct?
Yes, sir.
Understood. So that's why what happens is here this circuit becomes insensitive to supply variations. Even though your due to external conditions your supply can change, but your current won't change. And if your current doesn't change, your this thing won't change.
Gain.
Your value of GM won't change. Other thing, what the other one more thing this particular circuit is immune to is threshold voltage variation.
Yeah, PVT, no, sir.
Yeah, not like this circuit is not immune to all the process variations. Like if there is change in mobility, what we saw, the current in the transistor depends on ID, correct?
Yes, sir.
And ID is fixed. This ID is fixed to 200 microampere. Okay.
Yes, sir.
And what is GM?
Mu and COX. Oh, yeah. Two times of ID.
ID mu n Cox
WL.
mu by L. So if you are able to maintain the ID constant, if this
GM.
ID is constant, the GM will remain constant as long as there is either supply voltage variation or there is threshold voltage variation. There is no VT term in this, right?
Yes, yes. Yes, sir.
Yeah. So let's say if the threshold voltage of this transistor, the bias generating transistor and the input transistor are same, in that case there will be no variation in the gain due to threshold voltage variation or supply voltage variation. However, if there is a change in mobility, if the mobility changes, then there will be changes. You understand this?
Yes, sir. Exactly. Here
Yeah.
VT is immune.
It's immune
Not
to
me.
VT and VDD variations, but it's not immune to mobility variations. For
Yeah.
that, there is another circuit called constant GM circuit that you will learn in later classes.
Okay, sir. Definitely.
Okay. So, the benefit from going to this circuit is it provides you certain level of immunity from the environmental variations.
Sir, in this case, in the next question only, here instead of 0.4 mega ohm, they added one more resistor, sir.
Yeah. Okay, see. Let's try to see what is there in this also. We will have to work this out. Hmm.
Sir, can I have a doubt, sir?
Yeah, sure.
Sir, here in the current equation, what you have written is Vg minus IDRS whole square.
Correct.
We have neglected their Vt, sir. Is it
Sorry,
how?
sorry. Here we will have VT as well. Yeah.
Okay. Thank you, sir.
Yeah. So accordingly, the equations will be modified, but yeah, still that this ID will be a function of Vg, that won't change. So sorry, this was a mistake. Okay. Now, this thing is clear, right? What is the benefit from moving to the first circuit to the second circuit?
Yes, sir. Clear, sir.
Now we will see what happens when we move from second circuit to the third circuit. So, see, as far as your small signal is concerned, it's both the circuits are roughly the same. There is one, so in small signal, what you will have is there will be a 25 kilo ohm resistance, there will be a zero point 0.5 mega ohm of resistance, then there will be a 4 kilo ohm of resistance, and then there will be 1 by gm. And in this case, 25k, then 0.5 mega ohms, then there is 1 by gm. So this 0.4k is also very small as compared to this 4k is also very small as compared to 0.5 gm. So this circuit won't make much of a difference. In the common source side also, this C2 will get biased, so there is nothing to it, and you will have some value of RL, and here also some value of RL. Okay. So as far as your common sources, the small signal is concerned, both the circuits have same equivalents. Is this clear?
Yes, sir.
Okay. Now let's try to make the let's just focus on the this part. Okay. So we have these two circuits, correct? Can you see how I drew both the circuits?
Yes, sir.
Okay. Now, so we said that in this circuit, if there is a VT variation, as long as that VT variation is same in both the transistors, your circuit will remain immune to VT variation. Do you understand this?
Yes, sir.
Okay. Now let's say if there is yeah.
Sir, sir, in the first circuit, shall we neglect 0.5 mega ohms, sir?
Yeah, zero point 0.5 mega ohms directly go to the gate of the transistor M2,
Okay, okay,
and
okay, 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 okay.
yeah, and here also you can neglect. In fact, you can remove this.
Why so, sir?
So this also behaves the same way, right? So in the DC analysis, what will happen? This will become open circuit, right?
Yes,
And the current, the 200 microampere current, okay, when it comes here, it will have either this path or this path. So since this 0.45 mega ohm again directly goes to the gate of the M2, so nothing will flow in this. Okay.
yes, yes, sir.
And if nothing is flowing through a resistor, then there is no voltage drop across that resistor, correct?
Okay.
Yeah. So if you have any value of resistance, as long as it is not becoming equivalent to the gate resistance, which here we have assumed infinite, so any value of resistance for that matter in this path, it does not matter at all as far as
Okay.
your DC circuit is concerned. That 0.5 mega ohm resistor is put in place just for the purpose of small signal analysis, because when you do the small signal analysis, what happens is the this capacitor becomes short.
Yes, sir.
You have 25k over here, and then it goes to gate. Before going to gate, you have this 0.5 mega ohm. Now this resistance is put in place so that if there was, let's say, only 25k over here, okay, so the capacitance value now I hope you guys have studied the like you guys have encountered like calculating the value of these capacitances for uh, the corner frequency to be at a certain level, correct?
Yes, sir. We need to find out the V and R. No, sir. C1 should be much greater than much greater than
Yeah, yeah,
that.
yeah, correct. So if let's say this particular if this zero point 0.5 mega ohms and then it goes to this thing, right? Just a minute. Just a minute. My pencil got discharged. So 0.5 mega ohms and then there is 1 by GM. Now let's say if this 0.5 mega ohms was not there, in that case what would have happened? There would be a 25k resistor. Then there will be directly either in this case 4k plus 1 by GM, correct? Now this 1 by GM resistor plus 4k will be a very small value. And then there will be from input to the gate of the transistor, there will be a resistive division. And that will attenuate the circuit, attenuate the signal big time.
Yes, sir. That's why we need. Yeah.
Yeah.
So,
So to
okay.
avoid that, you need a huge resistance so that that resistive divider does not attenuate the signal significantly. You understand this?
Yes, sir.
Subarao, you also understand this?
Sir, zero point 0.5 mega ohms is in parallel with the gate and this junction, sir. So if we are taking parallel, then it will be very less, na, sir.
No, no. Zero point 0.5 mega ohm is in parallel with gate, but with zero point 0.5 mega ohm, there is series of 1 by GM. Can you see this?
Sir. Okay.
Yeah. So if this zero point 0.5 mega ohm is not there, then directly 1 by GM will come in parallel to the gate. Then your attenuation will be huge from input to the gate.
Okay. Signal will go through 1 GM to ground. Okay.
Correct,
If zero point
correct.
0.5 mega ohm is not there. Okay.
Yeah.
Okay.
And okay.
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 Okay. Thank you, sir.
Yeah. So let's come back to the biasing circuit issue. So, so before actually moving to this particular circuit, we will have an one intermediate circuit over here. This is 1 kilo ohms. There is one resistance over here, and then there is this. Okay. So let's say so what we discussed initially. So what we discussed initially, if there is a VT variation in both, let's say there is a VT variation due to process change or some temperature change, and as long as the mirroring transistor and the input transistor are in close proximity, they will face same kind of VT variation. Is this clear?
Yes, sir.
Yeah. Now, in that case, if the VT variation is similar in both the cases, the current mirroring happening from the gate, happening from the this transistor to this transistor will be exact.
Yes. Ignoring mismatches, no, sir.
Yeah, I'm coming to that. Now, let's say if there is a mismatch, that let's say uh, the transistor M1 and M2 we have, let's say there is a mismatch in VT of transistor M1 and M2 by delta VT. Okay. Then what will be the change in the current in the transistor M2? And let's say this delta VT is a small value. So to find out that change, what you can do directly over here is, let's say there is some delta VT over here, the change. Okay. So either there some small change in the VT of this particular transistor or the actual input, both of them will be equivalent, correct? Do you follow this?
Sir, repeat again, sir, one point.
Okay, in just a minute. So what we are trying to find out, if there is some change in the voltage, the threshold voltages of M1 and M2, and that change is delta VT, what will be the change in the current of transistor M2? Okay, that we are trying to find. That is the objective. So how I will approach is, I will try to approach this in the following way. Let's say we had this complete circuit transistor M2, and we actually applied, let's say in the small signal scenario, we applied some voltage Vs. What would be the current that will be flowing through this transistor M2?
Current, yeah, it should be Vs 1 by 2 mu.
Vs times Gm in small signal,
Oh, okay, yeah, yeah.
correct?
Minus, yeah.
Gm times Vs. Gm times Vs. Okay.
Yes.
Now, let's say, so this is what is this? This is the incremental current. You understand the meaning of incremental current?
Yes, sir.
That there will be actual DC that will be flowing through transistor M2. On top of that, there will be an additional current with the value Gm times Vs. Do you get this?
Yes, sir.
Okay. The same thing happens when there is a difference between transistor threshold voltages of transistor M1 and M2. Okay. First of all, assume that both of them have the nominal value of Vt and Vt. Okay. Then there will be some current, and this current, let's say, is ID. If the nominal voltage, if there is no delta Vt is exactly equal to 0, then whatever ID is flowing through this transistor will be exactly mirrored into this transistor as ID. Correct?
Yes, sir. In
If there
DC.
is some nominal increase in the threshold voltage of delta Vt, then what will be the incremental change in the current of transistor M2?
Sir, definitely it won't be same, sir. Uh, but I don't know the how it is
Okay,
different.
so how we can approach it is in the following way. So let's say this is a transistor M1 and it has threshold voltage of Vt. Okay, let's take another transistor. Let's take this particular transistor which has threshold voltage of Vt. Add a voltage source of delta Vt at the source of this particular transistor, and call this complete block as one single transistor, that is a mismatch transistor. If this has let's say you want, if you apply some VGS over here, yeah, at the terminal of, and now let's say you apply some VG, some VS at the terminal of transistor M1, what will be the current in this? Half mu n Cox W by L times VGS minus VT, correct?
Yes,
Whole
sir.
square. This is correct.
Yes, sir.
Now let's say the same voltage Vg and Vs I apply to the terminal of this modified transistor.
Yes, sir. Here we'll subtract. We'll get addition of source voltage, no, sir. So if we take a Vg minus Vs minus delta Vt, so we can the ID will be reduced based on that, sir.
Vt minus delta Vt,
Yes,
correct?
yes, sir.
So you can assume that for this modified transistor, your threshold voltage is delta, like additional, Vt plus delta Vt. You understand this?
Yeah, we can. Yeah, yes, sir.
Understood?
Yes, sir.
Okay. So, applying, so having a mismatch of delta Vt can be over here equivalently said as there is a voltage source of delta Vt that is applied in the leg of this particular M1. Okay. Do you follow this?
Yes, sir. Exactly. Perfect.
Correct. So
Yes.
now this whatever. So let's say this is a diode connected transistor. In This is a diode connected transistor that you get that you understand, right? M1 is a diode connected transistor, correct?
Yes, sir. Because gate and drain are getting the same.
Gate and drain are so in small signal, how will it behave?
Oh yeah, it would be 1/GM.
1 by gm. So you apply some additional delta Vt on this.
Yes, sir.
Okay. Now this delta Vt, where this delta Vt goes, it goes directly to the gate of transistor M2, right?
Yes, sir. It will come by. Yeah.
Okay. And mind it how it is different from the original small signal analysis. In original small signal analysis, this Vi is an AC source. Okay.
Yes, sir.
Okay. So this capacitance will be short. But here, sorry, I have drawn this wrong. Here, this delta Vt is a DC source. Once a mismatch has occurred, that will just remain over there. You understand this?
Sir,
Mismatch
mismatch.
mismatch won't change over the won't change frequently with a function of time, right? Let's say some edge has been edged off, and due to that there is a mismatch in transistor M1. That will just remain as it is for quite a long amount of time.
Yes, sir. Perfect. Yeah.
Yeah, so this delta Vt is a DC source. That Vi is an AC source. There is a short of capacitor, but here there is no short of capacitance. Okay, so here whatever delta Vt comes in, it will directly appear at the gate of the transistor M2, because there is nothing to go over here. This C2 is a open circuit as far as DC voltages are concerned.
Yes, sir. Perfect. Yeah.
Okay, so it will directly appear at the gate of the transistor M2.
Sir,
Now,
here. Yes.
if it directly appears at the gate of the transistor M2, so this is the equivalent of this, right? Let's say there is instead of Vs in the small signal analysis, I am applying DC voltage of delta Vt. Do you understand this?
Yes, sir.
Okay, now if there is a DC voltage of delta Vt over here, what will be the current change in the transistor?
Sir,
GM time?
yeah, GM times Vs only, but
GM times delta Vt, correct?
yes, sir. Yes, sir. Yeah.
Okay, so we saw that if there is some mismatch in the threshold voltage of transistor M1 and M2, that mismatch directly gets multiplied by the transconductance of this circuit, and comes as the change in current in the M2. Correct.
Yes, sir.
Now let's say here there is a mismatch in the second circuit. Let's draw a fresh one over here. Now let's say instead of in this circuit, now there is a mismatch. This is transistor M1, this is transistor M2. Now let's say there is a mismatch in this transistor, and the mismatch of delta VT. So how will it look? There will be this 1 kilo ohm transistor resistor. And then let's say this transistor has some GM and this value of resistance R, and there is a mismatch of delta VT. Okay.
Yes, sir.
Can you calculate quickly what will be the current change in this scenario now?
Uh, Sir, it should be here. Source degenerator.
Degeneracy. There is degeneracy.
Yes, sir. Source generation. Sir, it should be GM into
GM into
one. Sir, 1 kilo ohm plus
no. I'm talking about only. I am talking only about the current change. I am not talking about the voltage change.
sir, it should be delta VT minus ID into R 1 by
Delta E minus ID into R.
yeah, whole square.
No, no. This is a small signal analysis, right? Delta VT
Okay.
is a small value. So GM times this thing, right?
Yes, sir. Yes, sir. GM
This is
times VG.
into ID, correct?
Yes, sir. Yes, sir. Correct.
So what is from here ID you can calculate as GM upon 1 plus GMR times delta VT. Okay. In the previous case, what was the change in the current? When there was delta VT over here, what was the change in the current in ID in this case?
GM into delta VT, sir.
GM into delta VT. So can you see that if there is a mismatch between two transistor, here the current change is much lesser than the current change over here?
Yes, yes.
Okay. So this degeneration, so this is basically acting, so this the load, this 0.4k ohm resistor at the source of the input transistor is actually acting as a degeneration in the DC circuit of DC analysis of the circuit. Okay. And this degeneration makes this transistor immune to the VT variation between M1 and M2.
Yes, sir. Perfect.
Understood?
Yes,
However,
sir.
here, since there is no degeneration over here, then any mismatch between M1 and M2 will have more severe impact on the current of transistor M2. Understood?
Yes, sir.
Okay. Now you will ask why this 4 kilo ohm resistor is required. For that, what you need to understand is when you apply a resistor at the source of this transistor, then the overall, if this point this 4 kilo ohm is not, let's say you apply a resistor over here directly, okay, instead of having this let's say you don't have this 4 kilo ohm resistance and you apply a resistor over here directly of 0.4k. Okay, so in this case, can you see that the current that will flow through transistor M2 will be less than 200 microampere? Hello.
Sir, yes, sir.
Okay, so in order to provide degeneration, actually you have reduced the current in transistor M2, but you don't want that. So what you will do is, instead of tapping over here, where the voltage, let's say, is VGS, you will tap at a higher point where the voltage will be your VGS plus some current, 200 microampere times some resistance. Okay, so that you can regain that drop that you have got in the leg of the transistor M2.
Okay, here we're compensating the drop. Okay, with the help
Correct.
of. Yeah.
So that's why you have, instead of tapping directly at VGS, you tap at some higher potential so that you can compensate for the drop that you incur while putting degenerate resistor at transistor M2.
Mm-hmm. Yes, sir. Super.
Okay, so this circuit basically tries to implement degeneration in DC circuit, DC biasing, so that this transistor becomes immune to VT variation, and then in order to compensate the voltage drop that occurs due to degeneration, it adds another resistor in the M1 side, so that that loss can be compensated. Do you understand this completely?
Yes, sir. Fully. Yeah.
Okay. So these were the incremental changes. The first one was susceptible to both VT. The first circuit, that is this circuit, was susceptible to both VT and VDD variation. This circuit became susceptible to VDD variation and systematic variation in VT. Systematic variation, that means same variation occur in both M1 and M2. And the third circuit basically became susceptible to VDD variation, the systematic variation in VT of transistor M1 and M2, and became immune to some degree to mismatch in VT of transistor M1 and M2. So this is the benefit of going from first circuit to second circuit to third circuit. Is this clear?
Yes, perfect, sir. That
Okay.
is the reason why we are using current biasing instead of voltage biasing, no, sir. It
Yeah,
is immune
yeah.
to.
You want to make it immune to most of the so anywhere whenever you use resistive biasing, it becomes susceptible to these kind of external variations,
Yes,
extremely susceptible to that.
perfect. Yeah.
Any other doubt?
Sir, from week three, sir, could you please give any not exact problem, similar problem? If you solve means we'll get any idea while we are solving, sir.
No, my intent always is to solve different problems, but yeah, since you had doubt in these problems, so we took up these problems.
Yes, sir. Perfect, sir. I mean, in week three assignment is coming, sir. That's why assignment deadline is not completed. So we are doing, and we don't need exact, sir. We are getting somewhat different. We'll get a approach to solve. Yeah, while we are solving. If I get any doubt, I will go refer the video, and I will clear my doubts, sir. That's all.
Okay. Okay, so we will go through some a few problems, at least one problem that I have taken from a small signal analysis. And the concept that I will try to teach in this particular this particular question will be a very important concept that will always help you throughout the course. Okay,
Yes, sir.
so let's try to uh, go through this question. So this is basically this is uh, uh, circuit with one current controlled voltage controlled current source there at the output, and from input to output you have to find the gain, the input resistance, and the output resistance. Okay, and in second part of the question you have to find all of these. You have to find all of these when gm is in two cases, when gm is finite and when gm is infinite. You understand what the gm is? Gm is the transconductance of this particular circuit, this particular vccs. So let's try to find the gain first. Can you help me find out the gain?
Yes, sir.
Okay, so what will be the current in this branch? What will be the current in this branch?
Sir, V in minus VGS by R1, sir.
V in minus VGS R1. Okay. What else? How else you can write this current?
Means
Okay. Where will this current go?
okay. Here it is going to source, no, sir.
Yeah. So this same current will flow from the previous branch also, no? Because here at the output it's open circuit.
Yes, sir. Series, no, possible.
Yeah, correct. So this is equal to GM times VGS. Correct.
Yes, sir.
So what is VGS in terms of V in? VGS is equal to
V in by yeah, 1 plus DM.
just try to solve this equation step by step. So we can write V in minus VGS is equal to GM times R1 times VGS. That implies VGS is equal to V in upon GM R1 plus 1. Okay.
Yes, sir.
So you get the value of VGS. Now what is V out in terms of VGS?
Sir, we have to be resistance is not the open circuit. Now we can take it as
Let's say this is VGS. What will be the voltage drop across R2?
okay. R2. It's R2 by
R2 into.
yeah,
What is the current flowing through R2?
yeah, GM into VGS, sir.
GM into VGS. So what is the voltage drop across this?
Okay, GM into VGS into R2, sir.
Okay. So what is V out then? VGS minus this voltage drop.
Yes, sir. Yes.
Okay. So what is it? VGS minus
GM into
GM times VGS into R2.
yes, sir.
That is equal to VGS into 1 minus GM R2. Okay. Now, if you substitute VGS from this equation, what you get over here? V out equal to V in times 1 minus GM R1 GM R2 divided by 1 plus GM R1. Do you understand this?
Yes, sir.
Okay. So this is clear now. Now, what will be the gain if GM tends to infinity? What is the gain right now, first of all?
1 minus GM into, yeah, 1
V of
minus GM in
1 minus
GM into R2.
GM times R2
Yes. 1 plus GM times R1 divided by.
divided by 1 plus GM times R1. What happens if GM tends to infinity?
Sir, it should be minus R2 by R1, sir.
This becomes minus R2 by R1. Okay, now what is VGS? V in times 1 plus GM times R1. Correct?
Yes, yes, sir.
What happens when GM tends to infinity?
It should be 0, sir.
Is this equal to 0? So, does this thing looks familiar to you at all? Let's copy this circuit over there. So you are saying when GM tends to infinity, VGS becomes 0 and V out becomes V in times minus R2 by R1. Correct?
Yes, sir. Inverting amplifier. Yeah.
Inverting. Do you get this?
Yes, sir.
Okay. So the phenomena is, and on what principle does inverting amplifier works?
Means if in uh,
Op
virtual
amp,
ground, yeah.
yeah, virtual ground. When does virtual ground happens?
Okay, okay. Yeah, when input resistance is very high, so no current will flow into the op amp.
That is okay, but how does virtual ground actually comes when the op amp is in what configuration?
Ideal, sir.
No, okay, op amp is ideal, but when will virtual ground actually occur? Will there be virtual ground in let's say I have an op amp, there is plus, there is minus. Okay, will there be virtual ground between the positive terminal and negative terminal in this configuration?
Oh, no, no, sir. When
When,
feedback resistance, yeah, one feedback resistance and
which kind of feedback?
yeah, negative yeah, inverting.
Okay, negative feedback. So when there is negative feedback, and you know that when there is negative feedback, the system is stable. You understand
Yes,
this? Okay.
yes, sir.
So and what does stability means? If you give a bounded input, you are supposed to get a bounded output.
Yes, sir. Pole should
Okay.
be in right of plane.
Yeah, pole should be in left half
Left,
plane, not
left
right.
of plane.
Pole should be in left half plane. Other thing is the system. You understand BIBO, right? You have one study. You might have studied it in signals.
Yes, sir. Bounded input, bounded output.
Bounded input, bounded output. So let's say if there was any circuit that had a controlled source in it, okay, any kind of controlled source. Let's say a CCCS, CCVS, VCVS, and or CCVS. Okay, let's say there was any kind of controlled source in it, and that control source was packaged inside a negative configuration. Okay, and negative configurations are supposed to be stable systems.
Yes, sir. It will
Okay,
subtract output. Yeah.
so let's say it has a any kind of gain. There will be current gain, voltage gain, trans impedance gain, transconductance gain, any kind of gain this can be. So like let's say if there is any, let's say this gain goes to infinity. Okay, so if there is any disturbance, any input that is given to the system, what will be its output? If the gain is infinity, if the gain is infinity and you give any non-zero input to a system, to this circuit, what will be its output?
Yes, sir. I mean, it should be multiplication of the gain, no, sir. Vout is
Yeah,
equal.
and what is the gain?
Yeah, it should be infinity only, sir. Infinity
Yeah,
of everything. Yeah.
but I am saying that this particular circuit is connected in negative feedback. Okay, if the circuit is connected in negative feedback, it can't give you infinite output, right? Because the system has to be stable.
Yes, sir. It can't go beyond plus VSS minus. Yeah.
No, no, not plus VSS minus VSS. It cannot. It will give you some something that is dependent on the input. Some it will give you something that is linearly dependent on the input. Okay, it cannot give you and it cannot go unstable. It cannot give you infinite output. Okay, so negative feedback will behave in such a way that it's whatever this control source is, its input goes to zero.
Yes,
Okay,
sir.
that is what also happens in your inverting amplifier. Let's say this is an inverting amplifier, right?
Yes, sir.
Okay. Here, let's say there is no input for now. Now, let's say this voltage wants to change. Okay. And let's say this voltage wants to go to some positive value instead of zero. What will happen? This gain is infinite. This gain, what will be the, in which direction will the output go? Let's say the voltage wants to go upwards. In which direction will the output go?
Downwards, sir, because of the sign.
Downwards, correct? Now, if the voltage tries to go downwards, the output will go downwards. Now, if this output is going downwards with the resistor divider between these two resistance, this will again go downwards.
Yes, sir.
Okay.
Yeah.
So even if the this point tries to go upward, the negative feedback will make sure that this again comes back to the original position.
Yes, sir.
Do you
Correct.
understand this?
Yes, sir. Perfect.
So now this can be any kind of source. This can be a current controlled voltage source. This can be a voltage controlled voltage source. This can be like any, there are four control sources, right? This can
Yes, sir.
be any of the four. But if that particular control source is present in a negative feedback, it will always make sure that the input, whatever the input, in this case, the input is the difference between two terminals. Let's say if this was a current controlled voltage source, then the input will be the current going inside this particular branch. Okay, so whatever the input may be, it will make sure that that input goes to zero. Do you
Yes, sir.
understand?
Yes, sir. Yes, sir.
Okay, same things is happening in this particular circuit. There is a controlled source with a gain. There is a voltage controlled current source that is present. It has a gain of gm, and let's say this gm goes to infinity. Okay, what will happen is, let's say this voltage tries to rise above zero. We saw that the vgs will be zero. Okay, let's say this voltage tries to rise above zero. What will happen? What will happen to this current? Will it increase or decrease?
Yeah, it will decrease, no, sir, because
Will decrease. Okay, if it decreases, it will try to
Mm.
pull the current out of this particular circuit.
Yes, sir.
Okay, now if the current is being pulled, what will happen to this voltage that was trying to rise above zero?
Yeah, it will decrease, no, sir.
It will decrease. Okay, this
Mm.
means that this control source is fixed in a negative feedback configuration in this circuit.
Yeah.
Correct? So in this case, what happens is if the GM goes to infinity, the input of this particular controlled source will have to go to zero. Now, what is the
Mm.
input of this controlled source?
Yeah, yeah, yes, sir. Current also is VGS only, no, sir.
BGS. So, without even doing all this math that we did, if there was question was asked, what will be the VGS if GM tends to zero? All we needed to look in this question is whether this GM is in negative feedback. That we looked we'll try to see that if this particular voltage tries to go up, we'll see that. In what way this control source will act, and if it is trying to bring back the voltage down, that means this circuit is in negative feedback. If this circuit is in negative feedback and it said that okay, the gain of this control source is going to infinity, then the input will definitely go to zero. Okay, so you
Mm.
could have directly written that VGS will be zero when GM is infinity. Okay. Now, if VGS is zero, now if this condition is has occurred, what will happen is now this is zero. You can directly say, okay, if this is zero, the current over here will be V in by R1 because this voltage is zero, and since there is no place for this current else to go, the same current will flow through this, and there will be a voltage drop of V in by R1 times R2. So your output voltage is minus V in times R2 by R1. So you could have saved yourself from this huge amount of algebra.
Yes, sir.
Okay, so in similar lines, you will encounter many such situations where you will find negative feedback, and there quickly you can say that okay, what is the controlling input, and you just make the controlling input as zero, and you will get the answer very quickly. Let's try to one more example we will do based on the discussion we had right now, and then we will close this session. Okay, this is R1, this is R2, and here I apply the input Vn. Okay, now let's say I am saying what will be the output voltage if Gm tends to infinity. First of all, if there is any question where it's asked GM is tending to infinity, most likely that particular circuit will have negative feedback in it. Okay.
No.
How
Sir,
will
even
you?
if it is diode connected also, right?
Yeah, even if it is diode connected, if it is asking GM tending to infinity, most likely there is going to be negative feedback. So the first thing you are going to check in the circuit is whether there is negative feedback or not. Okay, in this circuit, what will happen? Let's say while checking the negative feedback, all the inputs have to be de-energized. Okay, you understand the meaning of this? All the input sources, the voltage sources have to be shorted. The current sources have to become open circuited while analyzing the negative feedback of the circuit. Okay, so you can make this, and minded, this is a small signal model.
Yes, sir. Yes.
This is a small signal model. The biasing has been taken care of. You need not to worry about that. So let's say this particular voltage tries to go up. Okay. What will happen is the in the current that is flowing through this. Hello.
Yes, sir. Sir, actually, MOSFET won't be conduct, no, sir, because gate is grounded, no, sir.
No, no, no. I said that this is a small signal analysis. The biasing has been taken care of. This is AC ground.
Okay, okay, sir.
Okay, we are just talking in terms of small signal analysis. Forget about large signal analysis right now. So let's say this voltage tries to go up. What will happen in the current that is flowing through this complete circuit?
Yeah, current will decrease, no, sir.
Current will decrease. Okay,
Hmm.
this current
Drain
ID
voltage.
reduced. Now, if this current ID has reduced, what will be the voltage at this particular node?
Yeah, it depends on the current only, no, sir. Vs is equal to ID into R2. So if ID getting reduced, so source voltage will get reduced.
Source
So
voltage
then,
got reduced. Okay, source voltage got reduced. Now, if source voltage is getting reduced, what happens to VGS of this transistor?
means VG is grounded. Yeah, minus Vs, sir.
Yeah, if source voltage is getting reduced, what happens to the VGS of the transistor?
Yeah, VGS is going to reduce, no, sir.
No,
VG is
no.
already.
VG is grounded.
Hmm.
VGS is negative of VS, and VS
Yes.
is reducing. So what happens to minus VS? If VS is reducing, what happens to minus VS? Minus VS increases, right?
Ah, yes, sir. Yes.
Okay. So,
No, sir. Write down and sir. It will be.
so let's say this is V2. Okay.
Yes,
V2
sir.
is trying to reduce. Sorry, V2 is
Hmm.
trying to go up.
Hmm.
That means ID is reducing. That means VS is reducing. That means VGS is increasing. Correct? Do you understand till this point?
Yes, sir.
You understand, right?
No, no, sir. Actually, I'm getting found out, sir. Here VS is reducing, no, sir.
Yeah. So
Then VGS.
let's say your VS is 2 volts.
Hmm.
Okay. What is your VGS?
VGS is minus 2 volts, sir.
VS is 2 volt, VGS is minus 2 volts.
Hmm.
Now VGS from 2 volt reduced to 1.5 volts. What happened to VGS?
Yeah, minus 1.5 volts, sir.
Minus 1.5 volts. So what happened to VGS? Did it increase or decrease?
Yeah. VGS increases, no, sir. Yeah. VGS increase.
The magnitude of VGS is reduced, but VGS is increasing, and we are
Yeah. In terms
instead
of sign.
in
Yeah.
VGS, not in magnitude. Okay, so VGS has increased. So what happens if VGS increases? What
Sir,
happens?
ID will. Okay, small signal.
Yeah,
Okay.
even in small signal, what is the current?
Sir, current is ID, no, no, sir.
Yeah, ID is equal to in terms of VGS.
Yeah, VGS equal to 1
GM
plus. Yeah, okay. Yeah. I'm
ID is
getting.
equal to
Yeah.
GM times VGS.
Hmm.
Correct. So if VGS is increasing, what happens to ID?
Yeah, ID will also increase, sir.
ID will also increase.
Hmm. Yeah.
Now
Yeah. Correct.
ID increase. So so what is this circuit trying to do? It is trying to revert back this reduction of ID. You understand?
Yeah. Here ID will increase, sir. Again, ID will decrease based on the. Okay.
No, ID has increased. Now, so what happened? There was some effect, let's say due to noise or any external deviation. The VT tried to increase. That means ID tried to reduce. That means VS tried to reduce. That means VGS tried to increase. That means ID tried. That means ID again increased. And if id has increased, then v2 again will start to reduce.
Fine, perfect.
Correct.
Yeah.
So like this circuit is trying to revert back to its original position. That means this circuit is in negative feedback. This circuit is a stable system.
Hmm.
Okay. Now, if the circuit is stable, in that case, if the circuit is in negative feedback and the GM is going to infinity, what will happen to the input?
In AC, sir.
Sorry,
In
we
AC.
discussed we discussed over here, right? If in the control in a controlled source, the input goes to infinity.
Hmm.
Sorry, the gain goes to infinity. What will happen to the input? The input goes to zero, right?
Yes, sir. Input goes to 0. Yeah,
Okay.
perfect.
The same thing will happen over here.
Yes, yes.
Okay. Now, what is the input to this controlled source?
Grounded, no, sir, here.
No, no, no. In the original circuit, this circuit we made
Oh,
to
VA.
negative feedback.
Yeah,
What
VA,
is
sir.
what? No, no. What is the complete input to the current source? What is this transistor? In small signal, what a MOSFET behaves like?
Oh, yeah, voltage control current source, no, sir.
Voltage
VN.
controlled current source. On
Hmm.
which voltage does this current source depend?
Yeah, GM into VGS. VN minus VS. That.
V in minus Vs.
Yes, yes.
If GM goes to infinity and the circuit we have proved is in negative feedback, so what will
Hmm.
happen to VGS? If GM is infinity,
Yes, sir.
what will happen to VGS?
Yeah, VGS is also infinity, sir.
No, no, no. That's what we said that this we proved that this circuit is in negative feedback.
Hmm. Yeah, actually, VN should be 0. But,
No, it's
okay.
not zero. V in is some voltage. V in. You have applied it. It's not zero.
Uh, if GM is infinity, what should be the VGS? No, sir, you're asking.
Yeah.
Sir, I mean, I'll come with, I mean, GM is equal to mu and C works W by L VGS minus VT, no, sir.
Okay. No. Just repeat what I have told till now. If the circuit is in negative feedback and the control source gain becomes infinity, what happens
Hmm.
to the input?
Yeah, input is 0.
Input has
Input
to
will
go
go.
to zero. What forget about the input of the circuit. Don't
Hmm.
concentrate on the input of the circuit is V in. I am
Hmm.
talking about what will happen to the input of the voltage controlled current source that is placed in the circuit.
Yeah, it will decrease, no, sir.
It
Yeah,
will go
in
to zero.
it will go to 0. GM into VGS, you're talking the current source across the drain terminal.
Yeah, this is the current source. GM into VGS is the current source, and GM
Yes,
goes
sir.
to infinity. VGS should be zero, right?
Yes, sir. It will go to down. Yeah.
How can VGS be zero? I am saying VGS.
Hmm.
I am saying VGS has to be zero, and VG is equal to VN. That
Hmm.
means what should be the value of VS?
Okay. Yeah. Yeah, it should be minus VN, sir.
No, no, VN only. No, VGS is VG minus VS. So
Yes, sir.
both have to be equal in order to VGS to go to zero.
Yes, sir. I mean, so VS value should be minus VN, I'm saying.
No, 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 V in, not minus V in.
Oh, okay, okay.
It's gate minus source.
Yes, sir.
Gate,
VN. Yeah, correct.
correct.
Yes, yes.
So
Hmm.
VS has to be V in order to keep the input of this current source equal to 0. So
Yes, sir.
this is again equivalent to virtual ground that we have. Okay. Basic.
Hmm.
Let's say in the in let's say this was the circuit. Okay, and you applied V in over here. In
Hmm.
order to establish the virtual ground in this circuit, what does virtual ground means? The controlling terminal of this particular op amp has to go to 0. For that, what you used to do? You used to say that, okay, if this is V in, since this controlling terminal has to go to 0, this will also become V in.
Hmm.
Correct. The same logic we have to apply over here. The controlling terminal is this VGS, and this controlling terminal has to go to 0. So in order to go to this to go to 0, Vs will also be equal to V in.
Hmm. Yeah, how it would be possible, sir?
And this circuit is a negative feedback. It will make sure that this happens.
Oh, okay, okay, yeah.
Okay, the circuit is in negative feedback, and the transconductance of this transistor is infinite. So the circuit will make sure that this happens. Otherwise, your current will blow up. And in negative feedback circuit, if you give an bounded input, you have to get a bounded output. Current can't blow up.
Hmm.
Okay. So Vs will be equal to Vin. Now, if Vs is equal to Vin, then this problem becomes very easy. What will be the current through the transistor?
Current is V in, yeah, V in into R1, no, sir. Source
Vin by.
one.
V
Yeah,
in
V
by
in by.
R1.
Okay, if this is Vin by R1, the same current will flow through R2 also, right?
Hmm.
If the same current is flowing through R2, what is the output voltage?
Zero. VDS, yeah, zero.
Huh?
VDS, yeah, VDS should be minus GM
What is this?
into.
This is AC ground. Not VDD, but AC ground. I am talking. What will be the incremental voltage at V out?
Sir, minus GM is infinity, no, sir. Infinity minus GM into
Oh,
R2.
okay. What will be the current through across R2?
V in by R1.
V in by R1, correct?
Yes.
So what is V out?
Minus V in
GM
by
into.
R1 into R2. Minus V in by R1 into R2, sir.
Correct. You get this now, that if the GM tends to infinity, the gain of the circuit can be directly calculated by two facts. One, the circuit, this transistor is in negative feedback, and if the transistor is in negative feedback and the gain of the transconductance of the transistor has gone to infinity, its VGS is bound to go to 0, and if its VGS has bound to go to 0, that means the source and gate have to swing equally. So if Vg is equal to Vin, Vs is also supposed to be equal to Vin. So from there you say that, okay, Vs is equal to Vin, and after that that's a simple algebra from there where you can find out V out. So this saves you, if you wanted to do it in conventional way, first of all, you will find the value of output voltage in terms of GM. Then you will apply your limit on of GM equal to infinity, and then arrive at this result that V naught is equal to minus R2 by R1 times V in. But if you are aware that this circuit is in negative feedback and GM has gone to infinity, then you can directly say that VGS has to be 0. This kind of intuition will help you throughout the course. There will be many questions. Now, after this, you are going to try to make various kind of control sources using a transistor. There, this concept will benefit you greatly. So, try to keep this concept in mind. Try to replay this video and see that, revisit this concept and try to solve the two questions that I gave uh, again for like with by yourself, and try to wrap your head around this concept. That will help you throughout the course.
Yes, sir.
Any other doubts?
Sir, any problem which covers week 3? Sir?
Week 3 we will cover on Monday, no?
Monday, sir. I mean, if process, I mean, I will work on it, sir. So, there is time, Saturday, Sunday, if possible.
Uh, no, no. Right now, work on the assignment that you have. The assignment of week 3 is out, right?
Yes, sir.
Yeah. So work on that assignment.
Yes, sir. Okay, sir.
Okay.
Thank you, sir.
Work on that assignment, and we will discuss your doubts regarding that assignment on Monday.
Okay, sir. Sure, sir.
Okay. Any other doubts?
Nothing.
Sorry,
Thank you.
sir, if we are using current mirror, it is related to week 3 only. Only I am asking about the clarity.
Sorry.
If we are using this
Current mirror.
current mirror,
Yeah.
then if the current is supplied to a other which is having W by L more, will it the current will change, sir?
Yeah, yeah. So you can change the current by changing the aspect ratio. Let's say this current I naught was being pushed into the diode connected transistor that has a W by L aspect ratio, and this goes to another transistor that has 2 W by L of aspect ratio. So here the current will be 2 I naught. So you can like copy the current in terms of multiples of this thing.
Sir, if we are having another transistor upon 2W by L ratio transistor, which is having more ratio, the if W by L is more, then the current will be which we current will follow which one, which we have to consider.
The diode connected one. The diode connected one, whatever, let's say there is I naught over here, W by L over here. Here, let's say there is X W by L. You only have to follow the transistor that is there in the diode connected. Based on the ratio of the aspect ratio of this transistor by this transistor, that ratio, in that ratio, the current will be copied. So the ratio is X between this and this. The current copied will be X times I naught.
Okay, okay, okay.
Yeah. Any other doubts?
Yes, sir. Perfect, sir. Alone, a lot.
Okay, so if there is no other doubt, we can end the today's session. Thank you for attending.
Yes, sir. Thank you so much.
Thank you, sir.